All right, we have one more chunk of questions here, 23 through 28. This is the 2014 released AB exam, and we're just right now doing the no calculator multiple choice question. So in number 23, it gives you a piecewise function. It's in two different pieces, and do you notice that something crazy happens at -1? It moves from a line to a parabola. All right, so if f is the function defined above, then the derivative there is. Okay, now let's think about this. Derivatives don't exist at corners or cusps. So we have to make sure that the slope is nicely transitioning. So the slope on the left has to equal the slope coming from the right. Right? So the limits on the derivatives have to also equal. So what I'm going to do, let me switch back to red here for you. I'm going to find the derivative of that left-hand region. It's the left because it's x is less than 1. And then on the right, the derivative would be -2x. Then I'm going to plug the -1 into both of those. So f prime of -1 would be 3. That's coming from the left. I'm not using the proper limit notation here because I'm trying to move this along, just like you would during the regular exam. If you plug -1 in here, you get 2. The slopes are not approaching the same value, so this is a corner, so therefore the derivative doesn't exist there. All right, moving on. Let f be this crazy function here. This is called a rational function. Which of the following is a horizontal asymptote? Now don't forget, horizontal asymptotes are all about the limit as x goes to infinity or -infinity. So when that's the case, you have three options or three cases to consider. If the degree on the top is bigger, there is no horizontal asymptote. If the degree of the exponent, the net exponent on the bottom is bigger, the answer is horizontal asymptote at 0. But in this problem, it's a little different. We have a square on the bottom and we would have a square on the top. If we multiply that out, if we FOIL it out, we're going to get, and I'm not going to do the whole thing, -12 x squared would be my term on the top. You see that? And then my term on the bottom would be 4x squared. Now there'd be extra funny business here, but as you know, when you're plugging infinity in, those don't matter anymore. So when the degree on the top is equal to the degree on the bottom, you use the ratio of the leading coefficients. So the answer is there's a horizontal asymptote at y equals 3. So that turned out to be a pretty easy problem as long as you knew what the definition of a horizontal asymptote involves limit as x goes to infinity, and you also realize that the degree on the top and the bottom are the same, and there's no reason to multiply that out. Don't waste your time, folks. Just those first two terms are all that matter. All right, so here we have a function according to x, and then a function u according to x, and they want you to relate those two, dy to du. So this is going to be dy dx times dx over du. All right, so we're going to need to get dy dx. That would be 2x minus 2. And then du dx, right, the derivative of u with respect to x would be 2. Now we flip it over. We flip over that du part. We flip that over, and it becomes a half there. And then we bring our 2x minus 2 in there. That ends up being x minus 1, which is the answer. All right, the next one. You look at this and you, oh my gosh, this looks crazy. Look at the bounds and, oh my gosh, is this like inverse tangent or something? What do you notice? This is just the derivative of an integral. They undo one another. The derivative of the integral, they just undo one another, and wherever you see the t, you put that upper function. It has to be on the upper bound, by the way. But that's an inside function also, so we got to do chain rule. It's an inside function. So we tack on, we multiply by the derivative of the square root of x. Now remember, the square root of x, you should probably memorize this derivative, honestly. Okay, so then if you take the derivative of that, if this is f, f prime would be 1/2 x to the negative 1/2 power. That's 1 over 2 radical x, 1 over 2 radical x. So the final answer is 1 over 2 radical x and then 1 plus x. That, because when you square a square root, you get that. So do you see that answer there? I do. I see it right here on A. All right, cool. So I think a lot of students would accidentally say C because they would have forgotten to tack on that derivative, to multiply by the chain. That's really important. We got 2 more questions. A particle moves on an x-axis left and right according to this lovely sinusoidal function over here. When is the particle at rest? Okay, so what are you thinking? Velocity has to be 0. Velocity has to be 0 for this thing to be at rest. So we better take the derivative of the position because that's velocity, right? So velocity function would be 2 pi cosine 2 pi t. You notice that chain that I put on the front? This was the chain rule of that inside function right there. Plus the derivative of 2 pi t according to t, with respect to t, would be 2 pi. Now we want to know when this thing is 0, so we set it equal to 0. So we have 2 pi cosine. We always try to move as quickly as you can. Be careful with your algebra. We subtract the 2 pi to the other side. Okay, I'm going to show my work here, although you might actually skip this step. Because at this point, you're going to divide by 2 pi and get negative 1 equals cosine of 2 pi t. All right, when is cosine negative 1? Well, I think about the graph, and I think about it bottoming out right here at negative 1 after pi radians, right? Because it's a 2 pi period. So I want to know, when is this equal to pi? Because that's when we'll have the cosine of pi equaling negative 1. So I set that equal 2 pi t equals pi. I divide both sides by 2 pi. Pi's canceled. T equals after 1/2 of a second. 1/2 of a second there. All right, one more question and we're done with this section. Now this may make your head hurt a little bit. These slope fields, these can be a bit tricky. Really, you want to look for symmetry. You want to look for symmetry. Like, for example, I notice right here that, by the way, this is 2, this is 1. So at y equals 1, x doesn't matter, first of all. So you see how it's completely dependent of x. And I also notice that the slope there is 0. In other words, dy dx is 0 whenever y is 1. And I look down here, and I can rule some of them out. You see, this letter C is dependent on x. When y is 1, we'd have different slopes. That's not correct. Same thing here. If you factor the x out, you get y plus 1. 1 is not going to cause, y equals 1 is not going to cause a 0 there, so I can rule that out. Now up here, if I factor the x out, I get y minus 1. If you plug 1 in there, you get 0. If you plug 1 in right there, you get 0. So we can't rule A out. Same thing for D and E. We can't rule them out. All right, so what do we look for next? Well, what I look for is that when y is bigger than 1, I notice, and by the way, and x is positive, I notice that we're getting positive slopes out of that. So when y is bigger than 1, and when x is positive, we get positive slopes out of it. So let's see. When y is big, and x is big, we get positives. Yeah, that works. So this one is still, a is still in the mix. All right, what about this one here? When y is positive, real big, and x is real positive, we also get positives. But then I realize something on letter D. I realize that it has an x squared in it, which means it doesn't matter whether you go left or right, you would get the same slope. Let me say that again. It doesn't matter whether you go left or right, you would get the same slope. So we ought to see symmetry left or right. So this thing ought to equal whatever's over here. This thing ought to equal whatever's over here, and it doesn't. So I can rule out letter D just from my understanding of symmetry. And then I'm on a roll with symmetry, and I'm realizing this one is not dependent on x at all. There's no x. There's no x. So if there's no x, what happens in the slope field is they will all be the same like this if there's no x, because it's not dependent on x, and that's not the case here. All right, so I've kind of ruled them all out, and I've got my answer as being A, and you can start to do this analysis here and start to see how this one continues to work in all four quadrants of this graph. 1, 2, 3, 4 regions of the graph, and you can check just for signs, the SIGN, of course, of the different slopes, and it'll work. All right, so that was a tough question, took quite a bit of analysis there, but hopefully if you moved along during the previous problems, then you would have plenty of time to tackle some of these more difficult ones. All right, I'll put together videos on the no calculator section, or I'm sorry, the calculator section, and that'll be exciting too. All right, good luck.